Okay, I'd like you to take a look at this set of equations. Notice they're saying incompressible flow in conduits and pipes. And one of the questions that I think somebody asked earlier in the quarter is, how could gas, which we know is compressible, um, how is it that we're treating it as being incompressible? Well, I didn't answer this question very well, I don't think, but the deal is that in these equations, we're talking about flow, whether the flow is compressible, not the substance itself. Now, most liquids are, like water, are essentially incompressible. Most gases are compressible, but I can't even write that word, it won't record. Anyway, most gases are compressible, but the flow of the gas is largely incompressible, and really what that means is that the density is constant. So when we talk about incompressible flow, what we really mean is that the density does not change as we analyze the situation. Okay, oops. So anyway, back to this, what I wanted to point out is that in this equation, we have steady state, incompressible flow, and what they're showing you is essentially, again, an energy conservation equation. So we've got point 1 on the left, we have point 2 on the right, and notice on the right what this includes is a term, H sub f, to account for the frictional losses. And again, this equation, I mentioned when I went through the Bernoulli equation that what they did is they divided through by rho times gravity, so that each one of these terms, the z term, the kinetic energy term, the pressure, the hydrostatic pressure term, are now all expressed in terms of a head. So this is some sort of pressure head, and that's why you get this term H sub f to represent the frictional losses. So anyway, so that's what this equation represents, is the expression of essentially the conservation of energy in terms of an equivalent head for each of the terms, for the hydrostatic pressure, for the kinetic energy. And I wanted to kind of show how those are also reflected over here when you talk about fittings. So they consider minor losses, the losses that you get in the fittings and the contractions and the expansions, and they're expressed in H sub f fitting. So this is really a head loss from the fitting, and look at the way it's expressed. It's expressed as a function of some sort of constant or characteristic value, C, times the kinetic energy term. Here's the kinetic energy term. And what they're telling you is the loss that you get is a function of that term. So the more kinetic energy you have, the greater the loss. And they show you down here that nominal value for head loss in well-streamlined gradual contractions is about 4% of the kinetic energy head. So you can see this represents one velocity head. Okay. Yes, and then over here, this equation shows you how you might calculate the pressure drop, or use the pressure drop in a horizontal fitting. So if the z term drops out in the equation, and the velocity term drops out, they say the velocity is constant. So if you have some sort of conduit that goes like this, so the cross-sectional area throughout the thing is constant, then you kind of say to yourself, well, the velocity is constant, but what happens is, and the z, the gravitational potential energy, will be constant throughout, but you'll get some sort of loss due to the frictional effects, and that is reflected in a difference between these, between the hydrostatic pressure terms. So this equation down here comes from. This equation comes from dropping out these terms, the z values and the v values, and you're able to compute the effective head that is causing or that represents the frictional losses, and is expressed in a difference in or a drop in the hydrostatic pressure from point 1 to point 2 somewhere along this constant cross-sectional area pipe.